Let's take a look at simple harmonic motion. So let's take a look at simple harmonic motion. One of the simple way to model simple harmonic motion is actually placing an object and actually rotating them on the disc and actually shining a light. So you can see that if you shine a light from here and the disc is rotating, the position of this rod will actually cast a shadow here. And then when this rod moves, this is rotating at a constant angular velocity omega, and you can see that the position of the rod will move from its position at the black spot to the position at the green. In this case, the shadow of the rod will move up and then move down to the middle. And then after that, when it moves all the way to the red position, the shadow will then move to the extreme end. So as far as simple harmonic motion goes, it will be moving as such. And if you were to plot the displacement versus the time graph, you will get a sinusoidal curve. And x0 is actually the amplitude. With x0 as the amplitude for the displacement. The displacement for simple harmonic motion is modeled as x equal to x0 sine omega t. And this formula is given in the datasheet. And if you want to find out the speed at which the shadow is actually oscillating, then in that case, we can have v equal to dx dt. And from then, you get x0 omega cos omega t. And I can also further differentiate the dv dt to get minus x0 omega squared sine omega t. And from these two expressions, we could now plot the graph of velocity versus time and acceleration versus time. And from there, we can now start to look at how velocity and acceleration varies with displacement. So the first is to continue from looking at this expression. You can see that your x0 sine omega t is in actual fact your x. So I can now take this part out and actually replace it with x. So A is equal to minus omega squared x. You can see that there is actually the AX graph. This relationship is the linchpin of the definitions of simple harmonic motion. If the exam asks you to define simple harmonic motions, then we will be saying that the acceleration is directly proportional to the displacement. And the second thing we will say is that the direction of the acceleration is opposite to that of the direction of the displacement. So we can see from here that when the displacement is positive, the acceleration is actually towards the x equal to 0 position, which is what we call the equilibrium position. Conversely, when the displacement is negative, then in the case the acceleration will actually be positive because it will now be also directed towards the equilibrium position. It's also important to note that at the amplitude position, the acceleration is actually the maximum. Let's now take a look at how velocity changes with displacement. This is the formula that is actually given in the datasheet. So you can just leave it off. So V is equal to plus minus omega square root x0 squared minus x squared. So if you were to sketch V versus x, you'll be getting an elliptical shape graph as plotted here. And the next thing to note is that when at the equilibrium position, when x is equal to 0, that is when the speed is actually the maximum. That is when the velocity is actually the maximum. So for the case of the shadow of the rod undergoing simple harmonic motion at the equilibrium position, the shadow is moving forward, so it starts from this point. So when x is 0, it starts from this point. Then when it goes towards the amplitude position, it will go to 0, and thereafter it will reverse its direction of the velocity. So the velocity will now be negative, and you will head back towards the equilibrium position, where the velocity will now be the maximum, where the magnitude of the velocity will now be the maximum, but pointing towards the negative direction. So it's negative x0. And thereafter, you will then move to x equal to minus x0, where in this case, you will find that its speed will end up at 0 here, 0, before returning back to the equilibrium position, where its velocity will become maximum again. Let's now use this formula from the data bullet to derive the kinetic energy of the body that's undergoing simple harmonic motion. If V is equal to this, half mv squared will be equal to this. And if you open up this expression, half m omega squared, x0 squared is the amplitude, omega squared is the angular velocity. And so this value is actually a fixed value. And it's subtracted, and you subtract it by half m omega x squared. X squared is the displacement. So in a nutshell, your KE will vary in accordance to the displacement. So using the velocity graph here, we could actually square the value. If you square the value and multiply by half m omega, we get your KE. So you can see that the velocity at this 2 point is 0, therefore the KE at this 2 point is 0. So at this 2 point, the velocity is both omega x naught. So if you decide to square them and multiply by half m, they will all end up at this value, which is actually your half m omega squared x naught squared. The graph of KE is parabolic since it's expressed in terms of x squared, and the shape of the graph will be as such. So when displacement is 0, which means it's at the equilibrium position, your kinetic energy is in fact the maximum. That is the total energy of the object undergoing simple harmonic motion. So, and the total energy must actually be constant regardless of the displacement. And this total energy will manifest itself as kinetic energy and potential energy. And knowing the green line knowing that the green line is the total energy, if we have to sketch the potential energy graph, it must be sketched in such a way where PE plus KE must give me TE. So from here you can sketch. So from this we can sketch the PE graph. Similarly, by looking at the mathematical expression, if we know this is actually the TE, it means this expression has to be the PE. By knowing the formula of the velocity expressed in terms of displacement for an object undergoing simple harmonic motion, we are able to derive the KE expression as drawn here. We are also able to determine the total energy of the object undergoing simple harmonic motion as well as the potential energy of the object undergoing simple harmonic motion. So from here, we're able to determine how energy varies with displacement. Now let us take a look at how energy varies with time. So we still start from V equal to x naught omega cos omega t. So that is the graph in green. We'll take the same process of squaring the velocity and multiply by half m. So from this, you know that, from the green graph, we know that the velocity is maximum here. So if you were to square it and multiply by half m, in terms of the kinetic energy graph, which is in red, the kinetic energy must be maximum. At this point down here, when the velocity is minus x naught omega, you will find that the kinetic energy will be maximum as you square it. And at this point here, again, the velocity is 0, so your kinetic energy is back to 0. And finally, when the velocity is maximum, the kinetic energy go back to being the maximum. Again, once you sketch the kinetic energy graph, we could actually draw a straight line based on the maximum KE, because the maximum KE is equal to the total energy. And once we have the total energy graph drawn, to draw the PE graph, we know the PE graph plus the KE must give us the total energy, which is the reason why when we sketch the graph, we know that when the kinetic energy is maximum, your potential energy must be 0. And when your kinetic energy is 0, your potential energy must be the maximum. And that is how we derive the PE graph versus time.